All right, so for this problem, we have a square single turn coil. So that's going to be this box right here. Okay, so this represents our coil. So let's write down our data. So they tell us single turn. That means how many coils are in the loop? One, right? So in this equation here, N is one, single coil. Single turn. Let's see what else. 0.2 meters on a side. So if this is 0.2 meters on each side, we can calculate the area, although we're not going to use this. But the area of this loop would be 0.04 meters squared, is placed with its plane perpendicular to a constant magnetic field. So it would be like this. Look, if this is our loop, so it's kind of hard to show this on a two-dimensional screen, but the magnetic field, for example, would be going like straight in or straight out. So it says here that the plane of the loop is perpendicular to the magnetic field. So here's my question for you. What's theta in our flux equation? What's that theta going to be equal to? The number one wrong answer would be, kids would see this. Oh, what does perpendicular mean? 90 degrees. Not for this problem. The theta for this problem is what? 0. It's 0 degrees because remember, what is the definition of this angle? The definition of the angle, it's the angle between what two things? The normal line to the loop and the field. So the normal line to the loop would be sticking straight out. The normal line to that loop is going straight in your face, and then the magnetic field is going either straight in your face or straight in, right? So the theta here would be 0. The angle between the normal line to the loop and the field is 0 degrees. Okay, so let's put that down. So theta here is equal to 0 degrees. And by the way, what's cosine of 0? 1. So that just goes to 1. The cosine part here, the cosine part just goes to 1. All right, what else do we have? In EMF, EMF is another name for what? That's voltage. Did I spell that right? What did I spell? Voltage. Delta V is EMF. So our voltage is 0.018 volts. E is the same as delta V. Okay, 18 millivolts is 0.018 volts. When the area of the coil decreases at the rate of 0.1 meters squared per second. Now look, the main idea for this chapter is that when your flux changes, so look at this equation for induced voltage. When your flux changes, you're going to get an induced voltage. How many ways can you change the flux? Well, the flux equation is BA cosine theta. In this problem, what is causing, so let me write it again. So flux is equal to BA cosine theta. In this problem, what is causing the flux to change? The B, the A, or the theta? The A, it says right here. The area of the coil is decreasing. So really, for this problem, our change of flux is going to be B delta A, right? But now here's where kids get confused. They're like, what's this? It's the area is changing at a rate of 0.1 meters squared per second. So who can tell me what to do here? Pick a time interval. What would be a good time interval to choose? I just choose 1 second. If you focus on a 1 second time interval, what's going to be your change of area? 0.1 meters squared. And it doesn't matter what time interval you choose. What if we would have chosen a 2 second time interval? Then what would have the change of area been? 0.2. And you'll get the exact same answer, right? It doesn't matter how many seconds you choose. So let's just choose 1 second, okay? Now, how do we solve the problem? They want us to figure out what the magnetic field must be. So to figure out the magnetic field, make some room here. To figure out the magnetic field, we're going to go like this. We're going to use this. Induced voltage equals N, change in flux over time. But what's our N? 1. That just set that equal to 1. Okay, what did we say about our change in flux? The change in flux for this problem is B times delta A, because what's causing the flux to change? The A. So it's going to be B delta A over delta T. And then now all you got to do is solve this for B. So that's going to be E times the time over the delta A, just algebra. So this is going to be 0.018 volts times 1 second divided by 0.1 meter squared. And then this comes out as 0.18 Tesla.